Tune in to see my new Porsche 911 GT3 RS and me draw a computer. Let's say you've been doing maths for a while now, and you've only been working with numbers, integers, positives, negatives, fractions, decimals, or whatever. Now letters have come into play, and I remember me as a little kid, I was thinking, letters, they have no place being here. What is this, right? And then you continue on and you get introduced to calculus in late high school, early uni, and now letters are everywhere and numbers are a thing of the past. They're gone, right? And if you've been doing any of calculus, you've probably been introduced to derivatives or integrals. And in my opinion, derivatives are one of the most important topics you will learn. And in this video, I will try in my own words to explain to you what a derivative is, why we use it, how we use it, and why it is one of the most important topics you need to understand as an engineer if you wish to succeed in your degree. Alright, let me explain. I'd like for you to think with me for a second and just imagine a car traveling in a straight line. This car may speed up, it may slow down, but what matters most is that this car is traveling a certain amount of distance in a certain amount of time. Okay, well, how would I visualize this graphically? Okay, I can plot my distance on a vertical axis and the time it took for this car to travel on a horizontal axis. And with this established, let's say this car travels a certain distance in about 60 seconds. And it looks like bro was hooning the night before. Now, looking at this distance profile, I'd say to myself, how fast was or is this car traveling? And that is where the derivative comes into play. Okay, question. How do we define speed? Well, speed is in units of meters per second, which is just how many meters were traveled per 1 second of time. Or visually, we can write meters divided by seconds, or a change in distance divided by a given time frame. But that just looks a lot like the formula for a slope, which we figured out how to use in high school. Alright, let's work with that. Take 2 points in our line. Say our car traveled 60 meters after 6 seconds and 30 meters after 3 seconds. We have our formula for a slope, input our values, and we're going to get that our car traveled 10 meters per second. Easy. It's that easy, right? No. Alright? Let's change our distance profile. What if our car has a distance profile more custom to something like a parabola? I don't see any easy straight lines or slopes. Do you? So what do we do now? Well, we can take the same approach, but we're not going to get our speed at a given point. What we're going to get is the average speed of our car over a given time frame, and we do not want that. We want the instantaneous speed. We want the speed of our car at a given point in time. Alright. Now bear with me, this is where things can start to get a little bit confusing. Now the process that we're going to take to find the speed at a given point in time is most likely is somewhat similar. We're just going to take 2 points on our parabola. 1 point at time t and 1 point at a time t plus h away, where h just means that our points are separated by a couple units in time. And they're both going to give us two distances respectively. Now a notation is going to come into play that you may have seen before and you're looking at and being like, oh my god, I'm scared to even understand what's happening, but it's not that difficult. This notation that I've introduced just reads as the limit as h approaches 0. And what this means is if I apply this term to our slope formula, we're just going to evaluate it as our separation in time h becomes smaller and smaller and smaller to eventually 0. And intuitively you're going to say, okay, well, don't our points just become 1? Essentially yes, but not that simple, but it's going to make a lot more sense once I do an example for you. But what I've just done is just found the rate at which a variable is changing with respect to something else. As long as the function is continuous, as long as domain, blah blah blah, you don't care about that. Most importantly, what you care about is what you'd see in a maths class and what you'd be tested on. And if you followed along with everything I've just said and it makes sense, you'll be fine. Hopefully. Or I'm just really bad at this. So what I've just done is derive the formula for first principles of a derivative, which is how every derivative of a function is calculated. And it's what you see in every introductory calculus class in late high school or early uni, and is the worst thing you have to do because it's that one test that you don't get a calculator. But if we go back to our problem with the car, basically what we do is if we wish to find the speed, just take 2 points and that are separated by a very small distance and just apply our formula for a slope as that distance gets very, very small, where our points basically become 1. And that's what a computer does. It it basically applies this formula but gives a value to that separation being like our points are separated by 0.0001 units, and they get a very good approximation that we can use because it doesn't really affect our data. But that's not what we do on paper. On paper, we have to do some algebraic simplification to actually get a function that represents the derivative, which I'll show you how to do. Okay, before I get into an example, I think it's best that I go over some terms and some knowledge and some theory, just so we're all on the right page when I go through this example. First of all, I hope you understand what I mean when I write a function, that I'm just writing the output number is equal to some number squared. What this means is saying our input number, x, determines what our output number is, our f of x. And you'll see on a graph that it's just graphing every output number depending on the input. Say if x is 3, it's going to give me 9. Say if x is 5, it's going to give me 25, and so on and so forth. That's all function is. It's the same as just saying, oh, if x is this, I'm going to get this. Or if this is this, I'm going to get this. We just write it in this generic form where we're just saying this output number depends on this variable or this number. That's all this is saying. If I write dy by dx, this is not the same as our slope delta y over delta x, because what delta y means is this is saying give me y2 take y1, just give me the change, the difference between them. What our d is saying, our differential, this is saying, okay, I want the infinitesimal change. I want the change as that separation between them becomes 0. So it's the limit as h approaches 0 with our change. That's what that is saying. That's the best way I can put it in my own words. They are different. This is more of an average slope. This is an instantaneous slope. All right? And this dy by dx is the same as if I were to write your f dash of x, because that just means the derivative of our function, or if I just say our y dash or a y dot. Usually y dot means a change with respect to time, and a y dash means a change in respect to space. Space is in like a position. Okay, now we can go on to the example. Right, let's do an example that encapsulates everything I've discussed in this video so that you have a full grasp of what I've been trying to explain to you. Here on this function, I have the graph of f of x is equal to x squared, where it's a simple parabola, where in the first quadrant, everything is positive. We don't have to worry about negatives, nothing. It makes it easy. And let's say we want to find the generic function that describes how this output is changing with respect to our x. Right? So what we would do, okay, we need 2 points at any point. Say one at point x and one at point x plus h, because we have that separation distance h, right? And it's going to give us an output with respect to x and an output at f of x plus h. Okay, with that, let's apply our formula that we derived. We're going to say, okay, our derivative, our f dash of x, not our slope, because they're different, because we are observing as h becomes smaller and smaller, our f dash of x is equal to the limit as h approaches 0, right? And then we're going to write our change in the output. Let's say our f of x plus h, take our f of x on our x plus h, take x, right? That's a formula that we're working with, but then we need to find what these outputs are. We have our inputs, but what will our outputs be? Okay. With that, we're going to say, okay, well, f of x we know is x squared, which we've written above. And then let us sub our input of x plus h in as well, and then that will give us x plus h is equal to x plus h all squared, right? Okay, now let's sub that into our formula. So that is equal, remember to always include the limit as h approaches 0. It is important. If you don't include that in a test, the teacher will mark you off and you will lose marks. And if the teacher's a prick, he'll just give you nothing for the question. It's happened to me before, right? to sub in our values, we're going to say, okay, limit as h approaches 0 of x plus h all squared, take x squared all on h. Remind you that the minus x and the x, they cancel out, so it leaves a h on the bottom. Okay, well with this, we want to simplify this, and the whole aim of any first principles problem is to get rid of this h on the bottom, because in the end you're going to sub in 0, because you're just observing as what happens when h becomes 0. And if you're going to sub in 0 on the denominator, you're going to get, well, 1 on 0, and that say leads to infinity, and it causes a lot of problems and asymptote. You just can't have a 0 in the denominator. You can't divide by a 0. We all know that, right? So we need to make it simpler so that h is gone. Okay, well, let's simplify this. We're going to say the limit as h approaches 0, and we can expand these brackets of x squared plus 2xh plus h squared, take x squared all on h, right? Further go, okay, the limit as h approaches 0 of 2xh plus h squared on h, observing that minus x squared, they cancel out, we can get rid of them. Okay, we can further simplify, writing our limit once more, right? Taking out a factor of h, we get 2x plus h all on h and a. Look at this, our h's are going to go. That's what we've done. So we wanted h to disappear from the bottom. And then now on our next line, we can write, okay, well the limit as h approaches 0 of 2x plus h. And then what we're going to do here is we're going to say, okay, let's apply that limit. We're going to watch what happens to this function as h becomes smaller and smaller to eventually 0. And you basically, it just means sub in 0. Say h is equal to 0 in the next line. And then you're just going to say, okay, well then f dash of x, your derivative, well, that's just equal to 2x. And voila, we've got our answer. That's as simple as this gets. This is the simplest way I can explain this. Of course, there are questions that get much harder and much more difficult, but for this video, I'm just going to keep it simple. And as you go on and as you go forth, you're going to notice that once you're done with first principles, you're going to learn that there are rules that we follow for derivatives where you never have to do this anymore. You can just do it much easier, because people have done first principles a lot and they realize there are patterns. And these patterns let you just do any derivative by following these rules. Now, I hope you followed along with the examples I just showed you, and all the concepts I tried to introduce in this video made sense to you. If so, let me know down below, but if not, I apologize, I did a terrible job. But also let me know if I did a terrible job. And make sure to like, comment, subscribe if you wish to see more. Alright, that's it for now. See ya.